Hello and welcome back to the Software for AI Optimization Summit. Today we welcome our third presentation from Michael from SigOpt. Michael, we're going to turn our videos off and go on mute, and we will come back online once the video has ended.
Hello, I'm Mike McCourt from SigOpt, an Intel company. 7 months ago, Intel acquired SigOpt with the intent of strengthening their commitment to the AI model community. Today, I'll be speaking on our work involving advanced techniques to accelerate model tuning. I'd like to thank the organizers for inviting us to participate in this Software for AI Optimization Summit. Today's talk covers 3 elements very quickly. First, some discussion of Blackbox optimization strategies that we have adapted for tuning hyperparameters at scale. Second, we'll discuss balancing multiple competing metrics and how this is important in real-world circumstances. And finally, some currently ongoing work involving model information being incorporated into SigOpt to help accelerate tuning. Before we start, I'd like to explain the difference between training and tuning of AI models. Today, we will only discuss how SigOpt guides the tuning process. Training a model finds the parameters, maybe the neural network weights or the cuts in a decision tree, which minimize the loss of a model for a given set of training data and a fixed set of hyperparameters. In contrast, tuning models finds hyperparameters which allow a model to perform in a production setting at a level which all the stakeholders find acceptable. The important distinction here is that where we train is not the same as where a model will be expected to perform. In fact, tuning AI models requires a more meta-level analysis of the problem, considering instead all possible modeling choices of interest in the process. These choices are often termed hyperparameters or perhaps free parameters. They may involve designs of the model, elements of the training process, or even how the data may be adjusted in order for the model to perform best. SigOpt is a software as a service solution, which provides the ability to conduct this tuning while still leaving customer training data, model information, and evaluation strategies behind the customer's firewall. Indeed, we only know the information which is provided to us, in principle, only the information about which hyperparameters we should be studying. We provide suggestions for new configurations. The customer evaluates them and tells us how these configurations performed. Based on this information, our optimization engine relays new configurations through our REST API. These new configurations are tested, we find out how they perform, and we continue this cycle over and over and over, yielding better and better models over the course of this process. To power this optimization process, we use a variety of black box algorithms from the optimization literature. Most notably, Bayesian optimization, aka model-based optimization, which is a sample-efficient strategy for conducting optimization of black box functions. Now, all of these strategies are quite powerful, but in reality, they're often insufficient for our production setting. First of all, we generally have very limited time for our computations, unable to spend the significant amount of time that some Bayesian algorithms require. We also generally want to have multiple training runs asynchronously running in parallel. Many of our customers expect this, but most evolutionary algorithms do not run asynchronously, and rather they prefer the batch setting. And in fact, many of our customers enjoy being able to edit the optimization domain or even update results if they found mistakes in their code. And most of the standard algorithms of interest in the literature do not support this behavior. Here we have a diagram of the standard Bayesian optimization workflow, whereby a customer reports new data and simultaneously requests the next point to sample. In the standard setting, all of these elements happen in an online or blocking format. If you're running this computation locally, this may not be a problem, but in the event where it's an API request, the fact that this next point's computation could take several minutes is a problem, as API commands cannot run for several minutes safely. Instead, here at SigOpt, we've split the computation into different elements. In particular, the customer sends one API request where they report new results, and instead of running the computation, this triggers the computation on a now offline set of machines, as denoted with the green color. This offline computation runs and stores these results in our suggestions database, which is then accessed in a subsequent API request where the customer asks for a next point. At this request, we look into the database, drag the relevant points which appear in the database, and then re-rank them based on the current status of the experiment. This allows different commands to occur in a parallel asynchronous fashion and still be working with the most up-to-date information possible. This also allows customers to update their experiment, including the data and the domain, and still take advantage of this re-ranking process and the ability to trigger next points in order to get the best results available. In the second portion of this talk, we ask the question, how do we satisfy multiple stakeholders within a company? In particular, this often requires balancing multiple competing metrics, which occurs because tuning models with scalar optimization is satisfying but often incomplete. It can be satisfying to believe that there is a single metric which perfectly defines success, but this is actually rarely the case. Real-world circumstances involve multiple competing metrics, potentially balance between high accuracy or low inference time, or maybe in a medical setting, we might be trying to maximize true positives while also trying to minimize false diagnoses. A lot of circumstances can arise, but in reality, what all of these are teaching us now is that in order to address multiple competing metrics, our goal must change. No longer are we interested in simply finding the answer. We now need to understand our options. What options are available in the modeling process in order to balance these competing metrics? One common strategy for studying the balance between competing metrics is to study the Pareto Frontier, which we display below for two metrics. More can be considered, but is difficult for the purposes of visualization. The question may be asked, can we find hyperparameters that maximize both accuracy and inference speed? The answer is probably not, but we can learn what is possible. Here we have a graph which represents two hyperparameters, the associated accuracy, which is shown here in contours with a maximum value here. The same set of hyperparameters, but now with speed graphed, is in this graph on the right. The maximum is over here. Here is the maximum for speed, but down here is the maximum for accuracy. In reality, they're not the same point, and if they're not the same point, then no, we cannot maximize both accuracy and inference speed. What we can do is find the points which trade them off efficiently, so that you can't get better at one without hurting the other. And that set of points is referred to as the Pareto Frontier, visualized here on this left graphic, where now I've plotted accuracy on the x-axis and speed on the y-axis. This is a graph of these metric values where the Pareto Frontier appears here with all the points furthest to the top and to the right. The green points represent all possible outcomes that can occur given this space of possible hyperparameters. These points are the points we're searching for because they give us the best possible performance. Finding the Pareto Frontier can be done in a few different ways. In particular, genetic algorithms are by far the most popular, but they also work best with a massive amount of experimentation or compute in the case of ML training. And in reality, for ML tuning, with a number of trainings required could go into the tens of thousands. This is probably impractical. Bayesian optimization, fortunately, has started to address this problem, first with a linear combination of metrics, later with some analysis of the Pareto Frontier hypervolume, and finally, and more recently, by adaptively enforcing artificial constraints. These model-based strategies are much more efficient than genetic algorithms. And in particular, you can take a look at our article in order to read more on this topic. Here we provide a visualization of how this adaptive artificial constraint strategy is applied within the context of Bayesian optimization. In particular, we have a simplified form of the results from this blog, whereby we have a performance metric and a stability metric, which we've just sort of estimated here and is not actually the full stability metric, which is why it appears so simple. If we look on our graph here, we have a very complicated Pareto Frontier, which appears in at least 3 pieces. And indeed, those 3 pieces are sort of represented here in the physical hyperparameter space. As we see this graph evolve here on the left, what we're seeing is this horizontal line where stability is being enforced artificially within SigOpt as a constraint. And then what we're trying to do is find the highest performance value, which still satisfies that given stability constraint. Now, the customer doesn't see any of this occurring, but they do get the benefit of being able to search what is a very complicated space and be able to yield a very fragmented Pareto Frontier without having to understand what's going on behind the scenes. Approximating the Pareto Frontier with 2 metrics requires many points. We are confident in our algorithm, which is written in this article and is proved effective in tests and in practice, but in our tests, we've also seen that moving beyond 2 metrics really requires a lot of points. And dealing with this in an ML tuning situation often proves infeasible, given the long training times associated with many ML models. So then the question may be asked, what can be done to manage this higher number of metrics? We propose 2 strategies which are available in SigOpt today. One is to enforce some metrics as constraints, and the other is to reformulate the problem so that success is independent of the number of metrics. The process of incorporating metrics as constraints involves turning a numeric metric into good enough. In this example that we show below, which is provided in this blog post, we're interested in maximizing accuracy and minimizing computation in the form of these max, but also limiting the maximum network size to 0.15 million or fewer neural network weights. Our algorithm, as described in this paper, modifies our computation to incorporate this constraint as information about it appears. And in particular, on this graph here to the left, you see what looks like a standard Pareto Frontier for maximizing this metric and minimizing this metric, except that several points here have been grayed out. These grayed out points violate the constraint, as we can see right here. And in reality, we spend as much of our time possible trying to avoid these grayed out results while still trying to find points that appear on the Pareto Frontier. An alternative strategy for incorporating many metrics is to change the concept of the problem. If a user were only interested in satisfying constraints for all metrics, then every choice of hyperparameters would be only satisfactory or unsatisfactory. There'd be no numerical values to consider over the course of the optimization. As a result, our model building process can actually be made independent of the number of metrics. We still need to build models for every metric, but we no longer need to consider all of the complicated possible interactions that happen between them. The result of this is that, in fact, no optimization is needed at all. In fact, we only require a search of the parameter space to find all satisfactory models. This is the idea behind our latest innovation, Constraint Active Search. You can read a workshop paper about it right now, and soon the ICML proceedings will be published, with the feature to be released on July 1st. The goal of Constraint Active Search is to explore the parameter space to give users actionable information as efficiently as possible. We provide here a visualization which shows the difference between different possible strategies, in particular starting with multi-objective Bayesian optimization. When the user imposes these constraints on the problem, it allows us to zone in on just this portion of the Pareto Frontier, ignoring this portion here and this portion there. In metric space, this is simply a wedge. And in parameter space, it's this shaded blue region. However, the Pareto Frontier is only this single line through parameter space. It doesn't actually study all the results which satisfy the constraints. Instead, we suggest that Constraint Active Search gives us the ability to explore this blue region very efficiently while still scaling to a higher number of metrics and providing actionable information. In the third element of our talk, we're going to describe some incorporation of model information to accelerate tuning. And in particular, this is a recognition of the fact that traditionally, our algorithms do not leverage information about customer models. This was actually one of the key elements of SigOpt, which allowed many of our customers to feel secure that their knowledge lives behind their firewall. However, increasingly, we have seen customers who seem willing to convey certain information to us, perhaps the type of model they're studying, maybe XGBoost or scikit-learn, the role of hyperparameters, maybe that something is a learning rate or a momentum, and maybe even elements regarding the size of their data, how many rows, how many columns exist in perhaps a supervised learning problem. We want to use this information, if possible, to give customers a better SigOpt experience. Our first batch of research on this topic has features specific to gradient-boosted methods. In particular, we focused on XGBoost and LightGBM, the popular open source packages for gradient-boosted learning. Our first work on this topic involves automatic hyperparameter domain selection. In particular, recognizing that at present, customers have to run this code in order to be able to tune their, let's say, XGBoost hyperparameters. In some ways, this isn't a problem, but it does require customers to make decisions as to what the bounds of the domain should be, as well as which parameters to study over the course of their SigOpt experience. If for no other reason, a good quality of life change would be to simply take in the knowledge, the fact that our model is going to be an XGBoost model, and instead make these decisions for the customers. Our second model-specific feature involves the development of special prior beliefs for XGBoost and LightGBM models. In particular, our computations are more effective with prior beliefs. These are knowledge about which hyperparameter values are likely to be good. This is information that at present we allow customers to construct on their own and pass to us in order to accelerate our computation by allowing our Bayesian models to be more accurate. However, in this gradient boosted setting, we can develop these prior beliefs ourselves and load these in for our customers without them having to request them. And there you have it. I would like to again thank the organizers for having us, and I would like to say that we are hiring. We have some new roles for engineering and product, and if you are excited about optimization and you'd like to optimize your career, please contact me, McCourt at SigOpt.com today. All right. Any questions about optimizing at scale, dealing with multiple competing metrics, or incorporating model information into the optimization process?
Hello and welcome back, and it couldn't have been better put than by myself. There are a couple of questions. Michael, can you elaborate more on the constraint active search topic?
Yes. A constraint active search is something which we're very excited about, but is admittedly very complicated. It's a rethinking of optimization in such a way that we recognize simply optimizing a function that you are studying today will not be enough to account for performance tomorrow. And so we try to explore the space in a more expansive fashion in order to understand what decisions can be made in order to achieve performance for tomorrow and all the days moving forward. We'll be presenting, as I mentioned, I think, a paper about that at ICML coming up shortly. So stay tuned for that, but you got a preview of it here today at this session.
Thank you, Michael. And a second question is, are there any use cases that you can speak of for SigOpt's work?
Yes, absolutely. I think that we have users from a wide variety of sectors. One of the most common use cases is in the tuning of hyperparameters for, I mentioned XGBoost models. We have a number of customers and users using us for tuning their XGBoost hyperparameters, such as learning rate or min split fraction or things like that. We also have a number of customers using us to tune their neural networks, in particular, again, learning rate or momentum or dropout quantities, trying to find the best performance or maybe the trade-off between highest accuracy and fastest inference time. We also have a number of customers in the financial sector who are using us in order to tune whatever they're tuning. They don't tell us, very secret. And we have some, and really I'm most proud of our academic users, people from a wide variety of sectors, including a lot of physical manufacturing customers who are using us to better develop their manufacturing processes, and they find Blackbox Optimization hosted by SigOpt to be useful for those purposes.
Brilliant. Thank you, Michael, so much. We're now going into a short break, but at 12 o'clock US Eastern Time, we have a panel. And then also at 1:25 p.m., that is US Eastern Time, we have virtual networking roulette, which gives you a chance to meet with the other attendees at random. So you get those chance interactions that you would get at a physical conference, but albeit virtually. And it would mean that you can meet people like Michael all the way in Honolulu in Hawaii, or Andrew, who's in Scotland. So we're really spanning the globe here. Thank you once again, Michael, and I look forward to seeing you all soon at 12 o'clock US Eastern Time.
Looking forward to it.
Brilliant. Thank you so much.